Okay. Okay, so welcome along, ladies and gentlemen, to your weekly SETI seminar series. Today we're very lucky to be joined by Michael Busch. Michael is a new SETI Institute principal investigator. He's been here for a couple of months now. Michael did his undergrad at the University of Minnesota, where he studied physics and astronomy. And then he did his graduate work at Caltech. He did his PhD under the supervision of Steve Ostro and Sheree Kulkarni. And the topic of his PhD, which is now actually available as a Google book, I understand it, is the shapes and sizes of near-Earth asteroids.
Should you actually want to pay money for a copy of my thesis, yes.
Yes, well, people might be convinced after this talk. So then Michael did a postdoc at UCLA and NRAL before coming to the Institute, as I mentioned, this year. He has a asteroid named after him, Asteroid 8129, which is a main belt asteroid. He's published many observations, radar observations of near-Earth asteroids, including 10115, 33342, 29075. Importantly, EV5, we might hear a little bit about that, 21 Lutetia, and also Phobos and Deimos. He's also published in the area of profitable asteroid mining, and has also used spin rates, derived spin rates of asteroids using radar speckle. Michael has also worked on SETI signal design, and I think I mentioned this in a previous talk. Before a previous talk, and he's been an advisor for the L1 signal, which is a crowd-funded active SETI search. So if you're interested in that, approach him after this talk, or you might address it in your talk, Michael. So please,
not this talk, but
not
okay.
not this talk. So see him after the talk. Please join me in welcoming Michael.
Thank you, and also thanks for the incredibly thorough introduction. So today I'll be talking about radar observations primarily of near-Earth asteroids, but I'm also going to give the bulk of my talk to background information on the near-Earth population, spacecraft missions to them, and also the near-Earth asteroid impact hazard, because motivation for why the public should be interested in what I do, as well as the scientific community. If what I'm saying at the beginning is too basic, please bear with me, but I should give a bit of background. So there are quite a large number of small objects in the solar system. This is a plot of everything out to the orbit of Jupiter as of about 2 weeks ago. So the sun's in the middle. The Earth was right there. We have since moved up a little bit in our orbit. Jupiter's up here. These two blue clumps are the Trojan asteroids, which are in orbital resonance with Jupiter. All the green dots are main belt asteroids, of course, primarily between the orbits of Mars and Jupiter. The blue dots are comets that just happen to be passing through. What we'll be focusing on today are the red dots. These are the near-Earth asteroids. We currently know about 10,000 objects on near-Earth orbits. In this case, we're defining them as things that are passing within 50 million kilometers of the Earth's orbit at some point in their own orbit around the sun. So while they can and do pass close to the Earth, most of the time, most of the objects are very far away from us. Some get closer into the sun than Mercury. Others get slightly further away than Jupiter. So we study the objects primarily when they come near the Earth, but they are spread throughout the inner solar system at any given moment. About 1,000, about 1/10 of the currently known population of objects, are bigger than 1 kilometer in diameter, which on the scale of this plot makes them about 100,000 to 1,000,000 times smaller than one of those pixels. So there's lots of empty space out there. But if we zoom way in with really good hardware, we can get ideas of their shapes. So this is a collage of small objects in the solar system which have been visited by spacecraft, put together by my friend Emily Lakdawala at the Planetary Society. I recommend her blog to you all if you have not read it before. Now, most of these objects were visited by spacecraft on their way to somewhere else. And most of them are actually not near-Earth asteroids. The 5 down on the bottom here are comets. I'm not going to talk about them. And the rest of here are mostly main belt asteroids. These 3 are near-Earth objects. But the near-Earth asteroids come from the main asteroid belt, so it's appropriate to group them together like this. On a time scale of a few million years, the current near-Earth asteroid population will be replaced by new objects from the main asteroid belt. And on a time scale of many billions of years, smaller main belt asteroids are being made from larger ones. We call this the collisional cascade. If you look at these shapes, pretty much the first thing you notice is they are not round. If you look at the largest 2 objects in the main asteroid belt, Vesta and Ceres, which are called dwarf planets, although they're also the largest asteroids, they begin to become roughly ellipsoidal. This is the definition of a dwarf planet. But when you get to something smaller, like Letitia, which is 130 kilometers across in its longest dimension, things get pretty lumpy. And you can see over the last 4 billion years or so, Letitia has gotten smacked repeatedly, excavating these large craters. The debris from collisions like that flies off onto its own orbits around the sun. We see these families of objects on similar orbits produced by this process. And the individual clumps of debris form the smaller objects here. On a time scale of 100 million years or so, something like the asteroid Toutatis, which is 4.5 kilometers long, will be destroyed in the main asteroid belt. On a time scale much shorter than that, on the near-Earth orbit, its orbit will get changed, and I'll talk about that more. But we have a surprisingly dynamic population here. If you zoom in further, you see that these things are indeed reaccumulated collisional debris. This is the asteroid Itokawa, which is that. I'm sorry, I keep hitting the switcher. That dot. We zoom way in. We see it looks like this. It's a pile. It's what we call a rubble pile. And most near-Earth asteroids are. You've got a large number of blocks of different sizes, ranging from about 100 meters across, the largest bits. Itokawa itself is 540 meters long. And the pieces range all the way down to, in this section, centimeter and millimeter size grit, and even smaller bits. Now, when I say blocks, and I point to things here, don't make the mistake of assuming they are single solid monoliths that you could smack with a hammer and they wouldn't break. They are only cohesive enough to have held together in the stresses that they've experienced since Itokawa got roughly its current shape. If you run them into the atmosphere, they can and do break into lots of little pieces. Which gets me to why people should care about near-Earth asteroids and scientific understanding of them. I mentioned that the near-Earth asteroid population gets replaced on a time scale of a few million years. That's because they're getting destroyed. They may break apart. Their orbits may become so eccentric that they fly into the sun, although that happens more often with comets. Or they may hit a planet. Occasionally, they hit the Earth. You see here a few examples. On the small size, it's not too inconvenient. This is an example from Illinois in the 1930s. An object about the size of my fist came in, was stopped pretty high up in the atmosphere, and then proceeded to fall at terminal velocity, which is only a couple hundred miles an hour. It punched through the roof of a car, through the back seat, and ended up lodged on top of the muffler. And this does happen every so often. But it's okay, because you can sell the car for more than the cost of getting a new car. Problems come in when we have larger objects. A bit over 100 years ago, an object perhaps the size of the building we are standing in, some tens of meters across, came in a place in Siberia called Tunguska. It did not stop until it was relatively low in the atmosphere, deposited most of its energy there. The objects are coming in at orbital speed, 15, 17 kilometers a second, 10 miles a second is a typical speed. They are, of course, getting slowed down by friction in the Earth's atmosphere, and all the energy gets converted to heat, light, and sound. Sound in this case means a shock wave so strong that it flattened an area, a very impressive area of trees. And if you have an object that's denser than Tunguska, but roughly the same size, it'll come down to the surface intact. And that's what happened at Barringer Crater in Arizona about 50,000 years ago. That object was made out of steel, which a few percent of near-Earth asteroids are. And because it's so dense, it came down nearly intact and excavated a crater, 50-meter object, and a crater is a bit over 1 kilometer across. And if you go out there with Peter and a metal detector, he will help you find pieces that are slightly rusted up. But that's because they've been sitting in the desert for the last 50,000 years. As the objects get bigger still, we start having global scale problems. The limiting case of this is the Chicxulub impact event in what is now the Yucatan Peninsula in Mexico. About 66 million years ago, there's currently debate in the scientific community as to if it was closer to 66 million years ago or closer to 65 million years ago, but we're quibbling about a few 100,000 years either way. An object 5 or 10 kilometers across came in and excavated a crater which is 180 kilometers wide. It's now buried under the last 60-something million years of sediment, but you can still see it in the bedrock. And if you go all around the world, you find down here what we call Cretaceous rocks, up here what we call Paleogene rocks, or also Ternary rocks, and there is this little layer in between. In that layer, there are very small bits of meteorite that were debris from the Chicxulub impactor. This was all first worked out by Louis and Walter Alvarez over at Berkeley, who were trying to understand why you see lots of dinosaur bones down here, but very few dinosaur bones up here. This is the mass extinction. It killed off all the dinosaurs except the birds. We would prefer to not experience that ourselves. Is there a question?
Yeah. Doesn't it have like a lot of iridium in that layer?
So iridium is an element which is fairly rare in the universe. It tends to, when you have a planet, the planet melts and differentiates and forms a nickel-iron core. The iridium tends to go with the nickel-iron and go down into the core. So it's very rare on the crust of the Earth in particular. It's relatively common in meteorites because most of them never differentiated to the extent that the Earth did. So that's one of the chemical markers you use to say the little bits we're finding in here are indeed pieces of meteorite as opposed to something from the Earth. So we would prefer that this not happen to us. But even far smaller objects can still cause fairly significant problems. So this past February, this was demonstrated far too dramatically. An object 15 to 20 meters across with a mass of perhaps 10,000 tons came in over Chelyabinsk, which is a city in the just to the east of the southern Ural Mountains in Russia. And the amount of energy deposited in this bolide over the city is equivalent to a few 100,000 tons of TNT exploding. Because 10,000 tons of material moving at 10 miles per second has quite a lot of mass and kinetic energy correspondingly. Now, this happened in early morning, so there's lots of videos from security cameras and from dashboard cameras of people driving to work, so you can go watch this event from many different angles on YouTube. But there's a bit of a problem. What do you do when you see a bright flash in the sky? I'm hearing lots of people say duck, but I also heard a few people say look at it. This is the problem. So the energy is here of the impact is primarily getting deposited pretty high in the atmosphere. The light reaches the ground in a very small fraction of a second. The shock wave is traveling at the speed of sound. It took some tens of seconds to perhaps a minute or two, depending on exactly where you're standing, to reach the surface. It blew out a very impressive quantity of windows. Peter Jennings, who is sitting back there, went over to Chelyabinsk and helped pick up all the pieces. So I have his souvenirs. So those broken windows were the primary cause of the injuries, about 1,100 people total, primarily minor injuries from flying glass, and a few tens of millions of dollars of property damage. And as this thing is going from east to west, the pieces travel primarily, that survive this whole process up in the bolide, are traveling primarily westward. The largest ones go the furthest and landed at a place called Lake Chebarkul, which is 70 or 80 kilometers west of town. I'm sorry, there's a typo down there. But I'm writing this in Roman rather than Cyrillic anyway, so I hope the Russians will forgive me. But you, of course, then can go and find pieces of that impactor again. Now I say you, in this case, again, it's Peter. Sorry to be singling you out here, but you did all this cool stuff. Forensics of the solar system. So Chelyabinsk started out as sort of a 15-meter stony object, fragmented and ablated, leaving primarily sort of 1 centimeter scale pieces, such as this one, which those of you here in person can look at afterwards. Something like this happens on the Earth once every few decades. Lest you think that Russia is getting particularly targeted, given this and Tunguska, remember Russia is a very large fraction of the Earth's surface. Most events like this happen over the ocean. The last time something like Chelyabinsk happened over the land was at a place in the Brazilian Amazon in 1930. Last time something bigger than Chelyabinsk happened, well, much bigger than Chelyabinsk happened, was, of course, Tunguska. You go back before the 20th century, we don't really have good data on events like this worldwide. And it wasn't until satellite monitoring came in the 1960s that we started to get good information globally. You can see here Chelyabinsk and the plume of the meteor imaged by a weather satellite. Again, it was just after sunrise. So stuff like this really motivates a project called Spaceguard, which was set up by NASA at the order of the US Congress in the late 1990s. The work on the Chicxulub impact was done in the 1980s. In the early mid-90s, it became clear that this impact hazard is something we should be understanding and eventually we'll need to do something about. So starting in the late 90s, a large number of survey programs, you see a few of them listed here, began surveying the entire large parts of the night sky, looking for at least the larger near-Earth asteroids that were bright enough to be observed. And you can see here that the discovery rate has kept on going up with time. And now we're at about 1,000 objects being discovered every year. This chart is given at 6-month intervals, so you see about 500 every 6 months. And if the Pan-STARRS project in Hawaii and the Catalina survey, which is telescopes in Arizona and a few other places, complete their current set of upgrades, this number will go up again. So we're discovering lots and lots of near-Earth asteroids. The important thing is the chart over here on the right. This is the discovery rate of large asteroids, bigger than about 1 kilometer in diameter. Remember I said there's about 1,000 of them. We know this because we've discovered almost all of them. This is the discovery rate as a function of time. You can see that it peaked around 2000, a few years after the start of the first large surveys, and it's been steadily going downwards since then. So we've discovered almost all of the 1 kilometer or larger near-Earth asteroids. That's the size where we start thinking about global scale effects of an impact. So in that sense, the impact hazard is resolved. We know there won't be any impacts in the next few hundred years that will cause global scale problems.
Except for long period comets.
Somebody has just said I should be worried about comets, and that is true. That, however, the impact rate of a comet of dangerously large size is about 1 per 100 million years, as compared to for near-Earth asteroids, where it's about 1 per million years. So we've gotten rid of something like 99% of the risk. We can say we don't need to worry about it in the next few hundred years. We have not lost the lottery. But we still are somewhat worried, obviously, about smaller objects, because stuff like Chelyabinsk is a particularly dramatic illustration. So there's now a project called ATLAS, the Asteroid Terrestrial Last Alert System, if I remember the fairly contrived acronym correctly. This actually was funded by NASA a couple of years ago. It's being assembled at the University of Hawaii. Should go active in the next couple of years. The goal here is to cover the entire sky every night. Now, I say the entire sky. I specifically mean the entire sky visible during the nighttime from Hawaii, which actually is an important restriction, because Hawaii is fairly near the equator. You don't miss too many objects at the South Pole, for example. And you can imagine putting another telescope in the south. But a certain fraction of objects that are going to impact the Earth come in from very near the sun in the sky. This chart is positions of meteors, so in this case small objects, 1 millimeter to 1 meter across, hitting the atmosphere. This is from a site in the northern hemisphere. The sun is plotted in the middle here. These are objects here and here that are on orbits very similar to that of the Earth, so either they catch up with us, or we catch up with them, or we're going in roughly the same direction around the sun. Sorry?
The sun is in the other block. It's in the helium section.
Sun is here, right?
No, it's 90 degrees.
I've gotten this chart mixed up. Oops. It's the advantages of having Peter in the audience. He catches me when I make mistakes. But the point is, there's a fairly large number of objects that come from near the sun in the sky. So you miss a fairly large chunk of them. But something like ATLAS can at least cover, and particularly if you put another equivalent somewhere in the southern hemisphere, you can get most objects like Chelyabinsk with at least a day of warning, and potentially as much as a couple of weeks. That's not necessarily enough to evacuate a city of 1 million people in a sensible manner. But it's enough to at least say, everybody, stay away from the window during this set of time. So that's the first reason people usually think of when they say the public should understand more about near-Earth asteroids. But I think there's another reason, which, as the impact hazard becomes better understood, becomes progressively more important. And that's spacecraft missions to near-Earth asteroids, because there have been quite a few. And since all of these missions so far have been funded by government space programs, they are fundamentally being paid for by the public. So you should know how your money is being spent. So I've put up some images here of various near-Earth asteroid missions. The first one, NEAR, also called Shoemaker, after Gene Shoemaker, the early expert on near-Earth asteroids and asteroid impacts, is now sitting on the surface of the asteroid Eros, which I showed you a picture of earlier. NASA is now doing a second asteroid mission called OSIRIS-REx, which is to launch in a couple of years. That will go to the near-Earth asteroid Bennu and pick up samples and bring them back to the Earth. ESA, the European Space Agency, is considering a sample return mission called Marco Polo R, which we'll know early next year if the mission is going ahead or not. That is to go to a near-Earth asteroid called 2008 EV5, which is shaped roughly like this, although it is not color-coded that way. That is the altitude of every point on the surface. And I can talk more about that in the questions if people are interested. And the Japanese Space Agency, JAXA, has done one asteroid sample return mission already, Hayabusa, and a second one, Hayabusa 2, is to launch next year, if I remember correctly. So the goal of all of these missions here is to bring back samples of near-Earth asteroids, particular near-Earth objects where we know the context of the samples we're getting as compared to meteors, which, of course, we have large numbers of, but it's often hard to say exactly where each individual sample came from, and also to bring back samples that have been protected as they pass through the Earth's atmosphere, which preserves their chemical structure and lets us get far more detailed information on the chemistry of these objects, which tells us a lot about the processes that formed that material early in the history of the solar system. as well as something about the process they have been through in the asteroid belt, and then when they got kicked into Earth-crossing orbits. So those are our sample retrieval missions. There's also recently been an asteroid flyby mission by the Chinese Chang'e 2 spacecraft, which was originally orbiting the moon. And I'll talk more about that towards the end of my talk because it is quite timely. And unlike these missions, it's already happened, so we actually have real results. If I were giving this talk 2 years from now, I would hope I'd be telling you far more about these two missions. There's also been discussions of far more ambitious missions. All those previous ones were robotic. There have been discussions of human missions. This is something the Obama administration in particular has been advocating, saying NASA should do a human near-Earth asteroid mission by the 2020s. I am paraphrasing a bit, but that is the gist of a few different policy documents. There is a severe caveat here, which is that NASA's budget right now, if you average over the entire Apollo program and compare it to the current budget annually, we're at about 1/2 as much money when you correct for inflation, which technology is better now, and there are some ways asteroid missions are easier, in some ways they are harder than lunar missions, but you're being asked to do a very ambitious mission with 1/2 as much money. So that places some pretty tough constraints on what we can do, which actually explains the two different graphics I have here. So I'll run through that briefly. So the proposals for sending humans to near-Earth asteroids they have a certain number of advantages. The first is it actually takes less fuel to get to many near-Earth asteroids than it takes to go to the moon. This may seem a bit counterintuitive. You're going to a near-Earth asteroid that might be a few million, 10 million kilometers away when you are there, and the moon is only a few 100,000 kilometers out. The reason for this is that the moon is a large object. It has lots of gravity. It requires quite a bit of fuel to land softly on the moon and to take off again. It actually takes less fuel to escape the Earth's orbit entirely and match the orbit around the sun of a accessible near-Earth asteroid. Now, these objects are very, very small. This is a concept art of a mission. The Earth and the moon are way in the background. The spacecraft is a bit less in the background, but the astronaut and the asteroid being visited are to scale. So this object here is about 30 meters across. The Chelyabinsk one, of course, would be one corner of it, but that's the scale of what you are dealing with. There's essentially zero gravity here. So it takes very little fuel to get on and off. I'm sorry. I keep going in the wrong direction. You also have the advantage this is easier in every way than going to Mars. The missions are shorter, it's easier to get to the targets, and again, you aren't working up and down a steep gravity well when you get there. There are some disadvantages, or at least challenges. It takes longer to go to near-Earth asteroids than it does to go to the moon. A lunar mission is sort of 1 week time scale out and back. For near-Earth asteroids, you're looking at 6 months or a year round trip, perhaps a couple of months at the target. We do worry about radiation. This is a problem for every mission beyond low Earth orbit and becomes more of a problem in direct proportion to how long you are outside the Earth's magnetosphere. And you do have this unusual challenge. The very low gravity I mentioned, which is measured in, say, 1 millimeter per second squared, 10,000 times less than the gravity we all are sitting in, unless somebody is watching this on YouTube while doing arcs in an airplane. You don't really land on a near-Earth asteroid. You dock with the surface. So how do you interact with a pile of rubble in microgravity? How do you get samples from deep inside an object? How do you prevent dust and grit from getting everywhere and seizing up the joints on your spacesuit? These are the sorts of challenges you have to address. And that imposes a certain degree of cost and risk to a near-Earth asteroid mission. Combine that with the current budget situation, and this motivated a new idea, which is to do the mission in the other way around and bring the near-Earth asteroid to the human. Now, given what I've talked to you about the impact hazard, you may be thinking this is not a very good idea. But it turns out to actually be the cheaper way of doing things. You go now to a very small near-Earth asteroid, something roughly 10 meters across. So it would fit in this room if you were to chop it up and rearrange the pieces. you return it to Earth-Moon space, but not to anywhere near the Earth. You bring it to the Moon, and you park it in high lunar orbit. And then the astronauts can go up there and visit it. And they are only spending a couple of weeks in space, and you can test all of the hardware you would need to do later human missions further afield. That is the sales pitch. This is an idea that was developed initially a few years ago at Caltech and JPL. This is some concept art that was put together at the time. It was then called the Asteroid Retrieval mission. The current branding, unless it's been updated again from NASA, is to call it the Asteroid Initiative. So you have a spacecraft which consists of a large fuel tank, a set of solar electric engines which provide high efficiency but take a very long time to fly anywhere. But that's okay. The robot can handle space for 5 years without needing oxygen or food or water. You have 2 large solar panels here, and then you have this complicated structure. So this is an inflated framework inside of which is suspended a bag. We made jokes about getting endorsements from garbage bag companies and so on, but you would more plausibly consider something like the material you make Martian lander airbags out of. It's very, very tough, and you know that it handles the space environment fairly well. You match the asteroid's rotation as best you can. You come up along that spin axis. You put the bag around the object. You pull it tight. You despin the whole system, and you've chosen your target such that it's going to make a close flyby of the Earth. You adjust that flyby geometry such that it passes very, very close to the Moon. It does a gravity slingshot maneuver, which is normally used to speed up spacecraft, in reverse, is slowed down and becomes captured into an orbit around the Earth, which is convenient to then be adjusted to have it be in orbit around the Moon. It is very, very important to make clear here, the objects we are talking about are something like 10 times less massive than Chelyabinsk, and will never be anywhere near any trajectory that would bring them to the Earth. And the engines would have to fire in exactly the wrong direction for 3 weeks continuously in order for them to be on such a trajectory. So the safety part of this mission was quite important in the design, which gets into one of the disadvantages where you bring the asteroid to. You can park it in high lunar orbit and ensure that it then will never hit anything near the Earth. It is still a bit of a chore to get out to high lunar orbit, and you have to deal with the radiation environment. There was initially some discussion of bringing it down to the International Space Station. Somebody pointed out that actually took way too much fuel, and also the ISS was very adamant they did not want a pile of rocks anywhere near the station, because it was never designed to have to deal with that. And then we do worry also from a science standpoint, although this is not primarily a science mission, the target is not going to be pristine anymore. You've put it into a bag. You've spun it down. This thing is probably a rubble pile, weakly cohesive. It's held together by slightly more force than gravity. But if you shred it to pieces inside the bag, it's going to be a little bit confusing interpreting what you've just picked up. And one of the main technical challenges right now is the design of that bag. In addition, there is an observational challenge, which is we still need to find more suitable targets. Right now, we know of 3. These are objects that are on accessible orbits that are well known, that we can say pretty definitively are low enough mass to be brought back, and will make that close Earth flyby we need in the 2020s. We can run things out further, and there are a few more targets, but we really want to find more, so you have a large range of objects to choose from. One more question, please.
Is there a particular type of asteroid? Like if you got a iron nickel asteroid.
This is a good question. So the goal is to find, ideally, something that's a carbonaceous chondrite. These are primitive objects that are relatively rich in water and also in carbon compounds. That's one reason why you'd want to get a large selection of objects, so you can pick the one with the composition you want. There is also discussion of what you would do with this thing after you've tested all the hardware for further human missions. There are these groups, Planetary Resources and Deep Space Industries and so on, that would like to buy this pile of rocks after NASA is done with it. And you can watch John Lewis's talk from last month if you wish to hear about how you can turn this pile of rocks into fuel and radiation shielding and air and water and so on. Or I can talk more about that in the questions. But since I have been going for a bit now, I'm going to have to switch over and talk about what I actually personally do. So we want to understand where these objects are in space. We want to, obviously for the retrieval mission, we want to know how big they are, we want to know their shapes. It helps to know how they're rotating. And that actually connects back to the asteroid impact hazard as well, because of an unusual bit of physics. So I'll talk about that for a moment. There is something called the Yarkovsky Effect, which was first worked out by this gentleman, Ivan Osipovich Yarkovsky, a bit over 100 years ago. The basic insight is that light is derived from the fact that light exerts pressure. We don't normally think about this in everyday experience, but light carries momentum and energy and can exert a force. So if you have an object out in space, the sun is shining on it, you have radiation pressure directed outwards from that incoming sunlight. But the object is also spinning, and there'll be a spot on the afternoon side, which is hotter than the morning side, because that side's been in the sun longer. And that's radiating more heat back out into space. Heat is, of course, in this case, primarily infrared light. It's carrying its own set of momentum. And so the asteroid gets pushed in a direction that depends on how it rotates, and with an acceleration that depends on its shape, its mass, and the details of how the infrared is re-radiated off the surface. More recently, the last couple of decades, we've understood something called YORP, the Yarkovsky-O'Keefe-Redzvetsky-Paddock effect. You can understand why we have the abbreviation. So this was the observation that if the object shape is irregular, the thermal re-radiation is not necessarily directed through the asteroid's center of mass, and it can be spun up or spun down. If it spins up too much, it bulges out around the equator, and you get a shape like this, which looks variously compared to a top, to a bran muffin, to a few other things. But it's bulging out around the equator because it's been spun up to the point that it's starting to have to deal with centrifugal force as well as gravity. And if you spin them up too fast, they will shed off material and form a satellite. Roughly 1/6 of the near-Earth asteroids, bigger than a couple hundred meters across, have satellites. Smaller objects, below about 100 meters, begin to have enough cohesion that by the time they spin apart, they are above their own escape velocity, and they fly apart completely. Quite literally, they explode because the sun is shining on them. Or the shape can reconfigure some other way, and the pattern of radiation pressure torques can change, and the object will spin back down. So you have this very complicated evolution, coupling the object's shape, size, orbit, and rotation and mass all to one another. So to understand this, both for individual objects, for predicting their orbits well into the future, both for spacecraft missions and for the impact hazard, and to understand this for the entire near-Earth asteroid population, we need a way of reliably characterizing a large number of near-Earth asteroids. And that's what I do, or at least try to do. And that's what I'll talk about for the rest of the talk. So the technique we use is to transmit a signal from a very powerful transmitter on the ground, either at the Arecibo Observatory in Puerto Rico or the Goldstone Deep Space Network site in the Mojave Desert. So the signal is transmitted from up here at Arecibo, bounced off the dish, and aimed at the target. With Goldstone, we can steer the telescope rather than just steering the transmitter, because Goldstone is only 70 meters across, whereas Arecibo is just over 300 meters wide. So Arecibo can only observe things when they are close to straight overhead. Goldstone can observe things throughout the day, but it's less sensitive. So they're complementary facilities. The signal that we bounced off the surface of the object is reflected. We record the radar echo on the ground, either with one of these telescopes or with a number of other facilities, particularly those operated by the National Radio Astronomy Observatory, where I worked until a few months ago. And by coding the transmitted signal, we can get information on a target's shape and rotation, as well as very precisely measuring its distance from the Earth and velocity relative to the Earth at that point in time, which all goes to predicting its trajectory into the future. I'm just going to give two examples of objects I've worked on recently. There was an object called 2012 DA14. I could go on about telephone numbers like happened during the introduction. We don't give them names because there's too many objects to have named them all by now. This one was discovered in February of last year by the La Sagra survey in Spain. And it quickly became clear that DA14 was going to make a very close flyby of the Earth in February of this year. So the distance from the center of the Earth is about 34,000 kilometers, which is actually closer to the Earth than a significant number of satellites. The geosynchronous belt of satellites is over the equator and orbits the Earth once every 24 hours, so it remains fixed relative to the ground. DA14 passed inside that ring, going from south to north, and did not pose a hazard to any spacecraft. Also, despite the timing, it is completely unrelated to the Chelyabinsk event. I mentioned Chelyabinsk was coming outwards from the sun. This one's traveling at almost exactly right angles to that. And despite the relatively close congruence in time, they were 500,000 kilometers from one another. Something like DA14 flies by the Earth actually fairly often, with something this size in one lunar distance every couple of weeks, perhaps. So this is merely a chance coincidence. The unusual thing is that we knew about this particular flyby in advance. Usually the objects are discovered on the outbound, and we don't have the chance to observe them. But we were able to observe DA14 with the Goldstone radar on 70-meter antenna at the Goldstone Deep Space Network site, and also with the Very Large Array in New Mexico, the Very Long Baseline Array, which has antennas scattered across the United States, and there's also a lot of optical observations from various facilities. And these are the radar images. Now, the resolution here is just about 4 meters per pixel, 3.75 if I want to be really precise, which is a little bit better than from, a little bit worse, I should say, than from the ceiling to the floor. The object, though, is only about 40 meters across in its longest dimension. So it's a bit grainy. But you can see it here, broadside, and then it rotated around. We saw it end on, and we saw it broadside again. So it's elongated by about 2 to 1, and it actually got torqued around by the Earth during its flyby. Because it's elongated, it's passing very close to the Earth, the Earth's gravity pulls slightly more on one side of the object than the other and torqued it around. And we've actually been able to start to measure that spin state change. The object may also have been slightly reconfigured because of that abrupt torque. That's something we're still investigating. So this is rather perhaps underwhelming because the object is pretty small in comparison to our resolution. So I'm going to show you another object. This one is Toutatis. It's been observed before with radar. It's close to a 4 to 1 orbital resonance with the Earth. That means its orbital period is close to 4 years. So it's flown by the Earth every 4 years since 1988, was discovered just after that 1988 flyby in early 89, was observed with radar by my thesis advisor, Steve Ostro, starting in 92, and I participated in the more recent observations. So the earlier Toutatis observations before last December, which was the last flyby in this current set, gave us this model of Toutatis' shape and told us the object is a bit over 4 kilometers long. But we didn't have the same resolution in the past as we have now, so we were able to get a picture that looks like that. This is a bit more impressive. You see the big end of the asteroid, you see the little end, you see the joint between them, and you see little things like that dot. That is a boulder, perhaps 10 to 20 meters across on Toutatis' surface. And we can now see structure like that. And we can track it as the asteroid flies by the Earth. It also became clear from our observations last year that this shape model, which I'm waving around, 3D printing is cool, by the way, is not perfect. It needs some improvement. We hadn't seen Toutatis straight along this axis before from this end. We'd seen the little end very well, but we hadn't seen the big end. So it ends up that the asteroid is not quite as tapered as this. It's a bit more blocky, and you can kind of see that here. And it also became clear that the joint is a bit sharper than it shows up here. We were able to say that with our observations, but in addition, because of the very long set of radar observations of Toutatis, we knew where the asteroid was in space to within a few hundred meters. And remember, the object is only 4 kilometers long. So uncertainty in where the object is far smaller than the object. We also knew how it was spinning, so we knew how it was arranged in space. Because of that information, the Chinese Chang'e 2 spacecraft could be pushed out of Earth-Moon space. It was initially mapping the Moon. The Chinese had parked it in orbit at one of the Earth-Moon Lagrange points, waiting for something convenient. And they were able to time it such that they pushed the spacecraft just out above escape velocity from the Earth. 6 months later, its spacecraft is 7 million kilometers from the Earth at the right location that Toutatis flew by it at about 11 kilometers per second. And they got this set of images as the asteroid flew away. And they were able to do this flyby, again, because we had the radar data, which we made public, saying this is where the asteroid is, and this is how it's arranged in space. And although they had not planned to get quite that close, they ended up passing just under 1 kilometer, about 800 meters, from the asteroid surface. Their plan had been to be slightly further away, because you can imagine if our spin model ended up being wrong, that would have been a bit awkward. But either way, radar observations like this, in addition to letting us predict potential Earth impacts and usually rule them out many decades to hundreds of years in the future, the radar data also lets spacecraft missions like this be possible. And I'm at 50 minutes. I could talk a lot more about what I do and about all the other stuff, but I will stop and take more questions. Thank you.
Have any questions? I'll get you to put up your hands. Michael, I'll just start with one.
Okay.
So you were recently at a meeting where you picked up some of these flyers. I know we left one of them out the front
yes.
there. Can you tell us?
So the International Astronautical Congress, which is a large aerospace meeting, took place in Beijing this year, sponsored in part by the Chinese Space Agency. While I was there, I had the opportunity to meet with members of the Chang'e 2 mission team, and they were kind enough to provide some of their data, which this particular image you can also get on the web. There are some restrictions as to how much people who are paid at least partially by NASA, such as myself, are allowed to collaborate with the Chinese Space Agency in particular. So we'll see how that plays out, but they have been doing very, very cool stuff.
Can you actually get or detect a reflection from, say, an asteroid 20 kilometers across the solar system, like in Superior Conjunction?
So this is actually an important question. So the signal to noise of a radar signal, that's how small of an object we can detect equivalently, although it depends on a few other things, depends primarily on the distance the object is from the Earth. Light spreads out usually as 1 over r squared of the distance. So we have 1 over r squared going out to the asteroid. We start with a very narrow beam, but it does spread. That's the SETI angle, actually. Most of my radar beams miss the surface of the asteroid and keep on going. And I think Jill Tarter, who's sitting back there, worked out at one point a few stars that we will have accidentally illuminated in a few decades. But the light that does hit the asteroid bounces back. It also spreads out. And so we lose out at the signal strength drops as the 4th power of distance, which is quite steep. Images like this, which have 4-meter resolution, the object has to be only a few % of the Earth's distance from the sun away from us. That's to say, a couple tens of kilometers. Toutatis was 7 million kilometers away. DA14 was obviously far closer. But more than about 10 million kilometers or so, it really gets hard to have 4-meter resolution. In the main asteroid belt, which is to say a couple of AU away, that's a few 100 million kilometers, our resolution might be 40 kilometers on the object, just because we need that much surface to get a signal we can detect. We can pick up the rings of Saturn, we can't pick up Saturn's smaller moons at all. There was some radar work from the ground on Titan before the Cassini spacecraft got there. That was mostly one side of Titan looks slightly more reflective than the other side of Titan to the radar, which is very useful stuff, but we're very limited by resolution, yes. So I can detect asteroids when they're very far away, but only if they're big enough. You did say superior conjunction. Remind me, that's the only object is on the other side of the sun from us? I always get that confused. We can't look directly at the sun for two reasons. One, the sun is a very loud radio source. You get too close to it, it overwhelms the signal from any reflection. That said, there have been radar observations of Mercury, which have been quite successful. That's how we knew there was ice in the craters at Mercury's poles. You can't get really much closer to the sun than Mercury does on the sky for the second reason, which is that the sun is really, really hot. If we aim the radar directly at the sun, all that heat gets reflected inside the telescope. And that can be really awkward for your instruments if they aren't designed to handle it. Some telescopes are, but with Arecibo and Goldstone, we do not look exactly at the sun.
I assume you're familiar with the B612 mission.
Yes.
What's your greatest hope or fear for them?
That they will make too much work for me. So for those who don't know, I'm going to jump back a bunch of slides here. The Spaceguard project so far has been primarily done from the ground, although some of these objects in here were discovered by the WISE spacecraft, which was in Earth orbit. The proposal from the B612 Foundation, which is named after the asteroid featured in Le Petit Prince book, is that asteroid does not actually exist. It is not a valid phone number, but that's OK. The goal there is to send a spacecraft to an orbit very much like that of Venus and look outwards from the sun. This has the advantage of you can see all the near-Earth asteroids, and you can cover that whole set of orbits very quickly. It has the disadvantage that you're pretty far away from most of the near-Earth asteroids that you're observing. So you're not going to find the really small ones. Their goal is to find objects bigger than about 100 meters, which happens to be about the size where you would actually talk about doing a deflection mission if you knew about an impact well in advance, as opposed to just evacuating the blast area. But there's still an awful lot of such objects. From the ground, we could discover them in a few decades. B612's Sentinel mission could do this in less than 10 years after launch. It's more expensive, but it's far faster. So that's a trade-off that we have to consider making. But also, if somebody does discover all these asteroids, there's going to be a lot more things for me to look at with the radar, which is both good and bad for me.
Michael, do you have any planned observations coming up shortly of near-Earth objects?
We have quite a long list.
Yeah. Well, what are you most looking forward to then in the next year or so?
Let me think about this. Problem is, I've been thinking so much about objects we have just observed, I've actually forgotten which ones are coming up immediately. There is one that's coming up next year, about 12 months, if I'm remembering right, which you've observed before. And if you get enough data on an object, you can actually measure that Yarkovsky perturbation directly, rather than having to infer it from the models. And that will be useful, because then we can actually calibrate how well we understand the shape and infrared coming off the surface. The telephone number on that one is 1998 WT24.
So could you tell us how powerful these transmitters are?
Arecibo transmits 800 kilowatts at 2380 megahertz, which is about 12.6 centimeter wavelength. Goldstone, we go at about half of that, 400 to 450 kilowatts. But our transmit frequency is higher, 8.56 gigahertz. So wavelength is about like that. We go through a lot of fuel for those generators at Arecibo.
So in that map of all the asteroids in the inner solar system, I noticed that it gets kind of seems to fade out toward the sun. Is that an observer effect, or is that real?
So there are some observer effects here. As I said, it's pretty hard to see things that are really close to the sun in the sky. That said, we do know from spacecraft that are dedicated to observing the sun, there are no large objects bigger than, say, about 1 kilometer on orbits that are entirely interior to that of Mercury. These have been searched for. They were called volcanoids. People thought they had seen them, but it always turned out to be internal reflections and so on inside the telescope optics. But it ends up that orbits that close in are pretty unstable because of the Yarkovsky effect. You're very close into the sun. You're getting lots of incident sunlight. The surface is very, very hot. And the object ends up being unstable to their eccentricity is getting increased. And as the orbit becomes more and more eccentric, one, it interacts more with Mercury and tends to get scattered out. And two, it gets closer and closer to the sun. So there's not much that stays inside the entire inside of Mercury orbit all the time. There are things, of course, that get far closer in than Mercury. One thing that isn't plotted here are these sun-grazing comets, of which we have known several thousand. I say have known because they keep falling into the sun and completely evaporating, and thus they aren't plotted here.
My question has to do with this very chart.
Okay.
I have two questions. The
Please.
first one is, the definition you gave for near-Earth asteroids was like anything that comes within 50 million kilometers?
50, yes.
50. And doesn't Venus come almost that close to us? It seems like a really large space to call, distance to call that a near-Earth asteroid.
Yes.
Why that particular number, 50 million?
It ends up being convenient. It excludes all the stuff out here, which just comes inside the orbit of Mars, and includes the stuff that is getting primarily perturbed by the Earth, and also for the ones that get close enough in by Venus. It is somewhat arbitrary.
Okay, the other question had to do with that chart that showed clumps of meteors entering the Earth's atmosphere, and
Which
showed the sun in the middle of it.
Well, Peter Jennings, who actually he makes these plots for a living, tells me that I got this one wrong. Where is the sun in this chart, Peter?
The two blobs near the center, one is the helium source of meteoroids and the other is the anti-helium source. The sun is very close to the center of one of those blobs. I believe it's the left one.
I don't understand the scale. What are these? I can't read the axes.
So this is going from the Earth's orbit plane around the sun to 90 degrees to that. So these objects are on very inclined orbits, and then these objects are on very Earth-like orbits that are in the same plane of the Earth around the sun.
Oh, okay, thank you.
But there's a clump that are coming straight at us from near the sun in the sky, which are the ones that are really hard to see from the ground.
Thank you. I'm interested in mining, and I'm wondering what steps need to be taken before they can really decide to mine? Do they have to go there and bring samples back, or can you tell what the asteroids are made of without going there?
So we get quite a bit of information on what the asteroids are made of by remote sensing. We call this staring at them from a long ways away. The radar tells us some stuff. It lets us identify ones that are made of metal because metal has lots of free electrons moving around in it, and it's really good at reflecting radio. Spectroscopy, splitting apart the colors of the light in the visible and the near-infrared, tells us more information about the compositions of the various types of objects that are predominantly stony. So we can say certain objects have lots of water in them, certain objects have lots of organics, and so on. We don't get really precise quantitative numbers, though. But for the initial products that people talk about mining, that's OK. It happens that 2008 EV5, which is now the subject of sample return mission by ESA for scientific reasons, might also be a good target for mining if you're willing to handle something that's 400 meters across. Because it's about 50, if we understand the infrared spectrum correctly, there's a fair bit of water in this thing, maybe 10–15% of its mass. It's not water held as ice. This is water held chemically bonded to the rocks. So that's the sort of information we can get. And we can get that on quite a large number of objects. We're making an effort to follow up more targets, particularly small ones, for the retrieval mission. If you bring back 1,000 tons of rocks, then you can do mining on that, at least at some scale. If you want to talk about processing things in situ and bringing only the products you care about back to the Earth, again, I refer you to John Lewis's talk from last month, which is in the archive of all SETI talks. And also to planetary resources and deep space industries. But in a sense, all of this is potentially product, because the products you're talking about initially are water for fuel and life support in Earth orbit, and sandbags for radiation shielding. And you can use pretty much anything for radiation shielding. All you need is mass. Lots of material to stuff into bags and place around your spacecraft, which is really expensive to haul from the ground. But if you can bring back 1,000 tons of material for a few $billion, the exact cost of this mission also needs to be understood. That's one of the reasons why there's a request in the NASA budget for engineering work, to make sure we actually understand how much this would cost us to do. But that is a pretty good investment either way, because it's a lot cheaper than bringing up the same mass from the ground. You launch 1 unit of spacecraft, and you get back 20 or 30 units of asteroid to play with. So, in a sense, this is asteroid mining. It's just the very most basic form you could imagine. And it would make future missions possible.
Yeah. Could you go back to the first slide showing all the asteroids?
This plot, by the way, you can get a new version generated every day.
Oh, really?
From the Minor Planet Center.
Yeah, you mentioned the Trojans up there in Jupiter orbit. It also looks like there are bulges right below that with the green asteroids. Yeah, and then one down below at the bottom. What's that, another resonance?
That is a 3-to-2 orbital resonance with Jupiter.
Okay.
Much like Pluto is in a 3-to-2 resonance with Neptune. Just these objects are interior rather than exterior. Oh dear, Jill has a question.
Well, I was surprised to learn that occasionally some of this stuff gets trapped as a pseudo-moon.
Yes.
So wouldn't that be a good target for capture and return or for mining?
Except except for a reason I'll talk about. So the context to Jill's question. There are objects on very accessible orbits relative to the Earth, which I mentioned. I talk about how we could capture one into orbit around the Earth. Sometimes that almost happens naturally. An object will approach the Earth and Moon, traveling very slowly, and will get temporarily caught into an orbit around the Earth. These are called temporary satellites or mini-moons, depending on who you ask. And they typically will come in and circle around in some complicated path for a few months or a year, and then they'll wander away again onto their orbits around the Sun. Several of these have been observed now, but most of them are very, very small. You might expect something 1 meter across to come through every year. Something like the 10-meter scale objects we're talking about for the Retrieval mission only come through every few decades. So it's a question of scale. If you are willing to bring back a baseball, you can grab a mini-moon almost all the time. If you want 1,000 tons of something, then actually going out onto solar orbit and grabbing one and tuning its flyby to actually get it really well captured, it's better than waiting for that 1 in 50 years event.
Almost perfect timing. Keep talking, Michael. I'm just collecting.
There's one more question here. You could have dropped the mic off as you walked.
I should have done that.
What about objects like the ISS? They're even considerably smaller objects. Has there ever been any studies in terms of, again, meteorites in that case there, the frequency or distribution?
How do you mean with the ISS?
There's a movie out now called Gravity.
Which I have not yet seen, but you can spoil it. Please, go ahead.
Oh, okay. But anyway, I would think that would be something that would be of great interest to NASA to know that if you're putting something expensive like that up there.
So there is quite a lot of work on debris, on small objects impacting spacecraft. There is a professor, Sigurd Klose, actually up at Stanford, who's been doing a lot of work on this recently. And among a large community of other people, many of whom were at the meeting in Beijing, because this is a concern to everyone who has satellites in orbit around the Earth. But right now, the primary hazard to satellites is not meteorites coming through, which this is still a problem, but far more of a problem are all of the bits of other satellites that are now flying around. Stuff in low orbit falls out of the sky on a time scale of a few years. The ISS is high enough up that it will stay up there for several decades, but they keep adjusting its orbit such that it does not decay. But that's not done with satellites that nobody's using anymore. And a lot of them are on really high orbits, which are going to stay there for a very long time. I mentioned the geosynchronous satellites. So I showed this chart of DA14 flying by the Earth. And I showed the geosynchronous satellite belt. What I didn't show is just outside that belt, there is another ring. which is all the satellites that used to be geosynchronous satellites that are dead. And they have just been pushed on slightly different orbits using the last bit of fuel, so they don't pose an immediate hazard to the satellites up there now. But every so often, satellites do run into each other. And of course, every collision makes a shower of debris, which is in orbit around the Earth. And that can cause that's the major source of worry for impacts on the spacecraft, is the junk that's in orbit.
As I said, let's not give away anything about that movie.
I don't mind.
Michael, we have a special
thank you.
SETI mug. It's a special design with two androids whispering the Drake equation to each other.
Oh, that is the Drake equation.
Yeah,
I hadn't seen that before.
Yeah. See,
okay.
you might find other things in there, and it hopefully it'll look great in your office.
All right. Thank you.
From tomorrow. Please join me in thanking Michael for his great talk.
Am I supposed to start drawing slips of paper here?
Yes. Does anybody have a final entry? If you weren't here and you're asking me the question, I'm sorry you have to come a little bit early.
I'm afraid that this question may have been too easy. The first one I got was correct.
All right, that's okay.
Evan Lim, grasshopper, correct guess.
Okay, we have
you get the
one.
book.
Evan Lim. Okay, great. One more.
Falcon 9 Dragon. That was not even actually an option. How did that happen?
Dragon X was an option. That was the tricky one. That was.
Another Dragon X. Okay, maybe I was just lucky.
SpaceX, if you want to use that, I've already copyrighted it now. Dragon
okay,
X.
grasshopper. Gert Gutstock, if I'm mangling the name, I'm sorry.
Good work, Gert. Come up and see us for your books. The rest of you can come up and ask Michael those burning questions that you didn't get a chance to address.
All right, I no longer need to be wired?
Yeah.
Okay.